Hey everyone, this is Dr. S, and we will be continuing our discussion on water's ability to ionize. Thus, for Lecture 3, the topic will be pH. The key learning goals today are that I want you to be able to comprehend titration curves of acids and bases, okay? And we will also be doing some calculations, and I want you to be able to calculate how to make buffer compositions so that you can manipulate solution pH. How could we begin without doing our molecule of the moment first? And today's compound is something called MOPS. MOPS is one of these so-called goods buffers. You'll see there's a lot in biochemical protocols and experiments because these compounds are really good at regulating the pH of a solution or media, and they do so without being toxic. So they're really great for fixing pH in cell culture and many biochemical applications. So let's pretend you and your friends, I don't know, Daenerys, maybe she's related to the Targaryens, maybe not. You're making MOPS buffers in the lab, and your target pH is 7.4, which we learned last week is physiological pH, a really good pH to do biochemistry experiments at. Both of you follow the protocol exactly. However, your buffer's pH measures to the perfect 7.4. Good for you. Daenerys, however, runs a little bit low, and when she measures her solution pH, it's actually 7.3. And hey, making buffer is boring, it's tedious, so Daenerys tells you that the difference between 7.4 and 7.3 is acceptably less than 5%, which is, the margin of scientific error usually. And she wants to head on out to, I don't know, burn down a town or something. Your gut, however, says otherwise. What I want you to do is to explain numerically, with numbers, why that difference between 7.4 and 7.3 is not as slight as she thinks. So mull that over, write out your answer, and we will be covering that first thing in lecture. Let's consider why MOPS is such a good biochemistry buffer, besides the fact that it's non-toxic. If we look at the molecule, it has two key functional groups. It has first a sulfonate over here, shown in red, and the sulfonate moiety or functional group is going to be moderately acidic. It has a pKa of 3.0. And I'll remind you that pKa is a measurement of how acidic or not a functional group is. The lower the pKa is, the more acidic it is. The higher the pKa, the less acidic it is. All right? So really what that sulfonate does is it just helps the molecule stay charged and very soluble across a wide range of pHs. It doesn't really do much beyond that. The morpholino is frankly something what we're more interested in. That is the thing that contains the tertiary amine functional group. This morpholino moiety has a pKa of 7.2. All right. Now, 7.2 is awfully close to our desired physiological pH being 7.4. But we need to take a step back and recall that the pH of a solution and the pKa of a functional group are similar but different. The pKa is the negative log of a moiety or functional group's acid dissociation constant. All right? The pH, that's the negative log of the hydronium content in the entire solution. pKa refers to molecules, pHs refer to solutions. Okay? So what I'm trying to get at is we can add in MOPS into a solution of water, and it's not going to magically become 7.4 or even 7.2 for that matter. It's going to be close, but we need to learn how to manipulate this to get the buffer dialed in to our desired pH of 7.4. And that is what we are going to spend the next few slides discussing. Think back to last lecture as well as general chemistry that acid dissociation is an equilibrium process. The stronger the acid is, the more we will favor the formation of dissociation products, such as hydronium and whatever the acid's conjugate base would be, in this case, A-. This also means, said another way, that the stronger an acid is, the larger its dissociation constant, Ka, will be. And Ka is simply the ratio of the concentration of products over the concentration of reactants. And as this number skyrockets, we're dividing a big number by a very small number, and hence Ka is going to be very large. Okay, stronger the acid, the larger the Ka. And this is where I think a lot of people can get confused. The reverse becomes true when you take the negative log of everything. Okay, the pKa of a functional group is equivalent to the negative log of its dissociation constant. So the stronger an acid is, the smaller its pKa will be. Okay, make sure you don't mix that up. It's really easy to do that. Now, I'm about to blow your minds. When you were in Gen Chem, probably, you may have learned that a strong acid is an acid that fully dissociates in solution. 100% ionization into H plus and A-. Well, I want you to think about that for a second, okay? What would be the Ka of an acid that fully dissociates? Remember, if it's pink, that means it's important. Look at this equation, okay? And ask yourselves, what would happen if HA was 0 and H plus and A minus was whatever number HA used to be? Let's say it was 100 or affinity or a mole. I don't care. All right. What would the Ka equal? Think about that for a second. All right. Let's take a step back and reacquaint ourselves on how we can use pKa to calculate the pH of a solution that is acidified with, let's say, a weak acid. And in this case, we will be determining the pH of a 10 millimolar acetic acid solution. ACOH is a very common abbreviation, if you will, of acetic acid. And the pKa of acetic acid is 4.76. We are going to use that number in a little bit, but first we're going to do everyone's favorite thing, which is an ice chart. We have to do an ice chart when calculating the pH of weak acidic solutions. All right, so initial, change, equilibrium. Those are the items we will be tracking. I've drawn a table like so. I like to draw a little line down over here between separating the reactant from the products. Okay, you don't have to. And let's just go through row by row and apply what we know and what we can infer to our ice chart. Initial conditions for HA, our weak acid, acetic acid, that is going to be absolutely 10 millimolar. But if you noticed, I used the units molar in the ice chart and I converted it accordingly, okay? You're just going to have to trust me on this. You want to do ice charts in molar. Just do that, please. All right, so 10 millimolar is equivalent to 0.01 molar. Nice. Now, the next question is, what's the initial concentrations for H plus hydronium and the conjugate base, A minus, in this case, acetate? Well, those are both going to be 0 because we have not dissociated anything yet. So pretty straightforward so far. Nice. Next row, the change. We know that acetic acid will rapidly dissociate, but it will only dissociate by a little bit, and that little bit is an unknown amount. So we're going to denote that as minus X molar because the concentration will be decreasing by that amount. And since acetic acid is a binary acid and it's dissociating, we're going to get positive X equivalents for both H plus and A minus. Nice and nice. The equilibrium row, we're going to put it all together. The concentration of acetic acid at equilibrium will be the starting amount, 10 millimolar, minus a certain unknown amount that we have to figure out. And that's going to be expressed as 0.010 molar minus X molar. And both H plus and A minus will increase by an amount of X. So it's going to be 0 molar plus X molar. Hence, they will both be X molar. And our goal here is to calculate what is X. Once we know what X is the H plus concentration, and we can convert that to a pH. So what we need to do is take the values in the bottom row and apply this to our equilibrium expression. And that is going to be Ka, constant of dissociation of an acid, equals the products over the reactants. So that's going to be H plus, which is X molar, multiplied by A minus acetate, also X molar, all divided by the reactant term, 0.010 molar minus X molar. We're going to make a few changes and substitutions here to make this calculation for X more doable. So right off the bat, notice how all this ratio equals Ka. I never gave you Ka. I gave you instead the pKa of acetic acid. And luckily, those two items are easily interconverted. And the way you do that is you go Ka is going to equal 10 to the power of the negative pKa, which in this case is negative 4.76. So we will put that into our calculators. And voila, the answer is 1.74 times 10 to the negative 5, no units. Okay, let's hit pause here for a second and ask ourselves, does this number make sense? Okay, I will remind you that acetic acid is a weak acid, and weak acids only dissociate by a small fraction. I'm often talking way less than 0.1% dissociated, which means that a solution of weak acid at equilibrium is going to contain mostly reactants, all right? And that is going to manifest in the Ka as a very small number because the amount of reactant, which is going to be in the denominator, that is going to be a huge number. And the numerator corresponds with the products, that's going to be a small number. And a small number divided by a big number is going to be a very small fraction or decimal or what have you. And check it out. We're talking 1.74 times 10 to the negative 5 for the Ka. That's a really small number, which means we're dealing with a weak acid here. So it makes sense. If this were a big number, we probably did this conversion up here incorrectly. So let's go on ahead and substitute in our Ka that we just computed. 1.74 times 10 to the negative 5 equals yada, yada, yada. We're going to make another alteration here that's really more of a quality of life adjustment. It's technically not necessary, but I recommend you do it. We're going to, again, think about how what we're dealing with is a weak acid. A very, very small amount of hydronium will be generated because the dissociation is largely not favored in equilibrium conditions. So if X is really, really, really small, if we subtract 0.01 molar from a really small number, it's probably still going to be really close to 0.010. All right. That difference is going to be within scientific or measurement error. So we're going to do a little cheat code here, and we're just going to forget about this minus x. And that's not something you can normally get away with in math, but this is the only instance that I'm aware of that you can just drop an x willy-nilly, so I say go for it. And this is already looking like a more manageable problem to solve. So let's try to clean this up a little bit, all right? 1.74 times 10 to the negative 5 equals x squared molar squared over 0.010 molar. Okay, we can get rid of this unit like so. And so now this is just algebra at this point. We want to isolate x to solve for x. So we can do that by multiplying both sides of this equation by 0.010. And I'm going to move over to this side of the screen. And this, you technically don't need a calculator for it. You're just moving the decimal place over by 2. So that's going to be 1.74 times 10 to the negative 7, like so. Equals x squared. So now, to find what x is, we just square root all of this, and that comes out to x equals 4.17 times 10 to the negative 4 molar. Okay, we're almost done. This is the concentration of H+. Because let's consult our ice chart again, X equals the concentration of both A- and H+. Now that we have the concentration of hydronium, we can convert that to the pH, which is what we've been after this whole time, by using negative log 4.17 times 10 to the negative 4 molar equals 3.37 pH units. That is the answer. Now, there's a few conceptual takeaways I want you to really appreciate. It's a really big misconception that, again, people think if you add in a weak acid, a weak base, the solution pH is going to immediately approximate the pKa. And we're like kind of in the ballpark. I wouldn't say we're that close, honestly, because remember, pH is a logarithmic scale. But the important thing to appreciate is that the pH wasn't automagically 4.76. The important thing here is that you now have a systematic way of going from the concentration of a weak acid, its pKa, and calculating the pH of the ensuing solution. So I hope you appreciated this ice chart refresher. That was a lot of work. Dust yourselves off, pat yourselves on the back, and let's barrel on ahead because ice charts segue really nicely into further untangling the relationship between pH and pKa. And this next slide is all about buffers, which builds nicely off of this concept. I want you to think about the acetic acid solution that we made in the previous slide. I'll draw a beaker over here. I'll fill it with HAC. That's another shorthand or abbreviation for acetic acid, by the way. And ask yourselves, what is the chemical makeup of this solution? And we can represent the ratio of reactants to products in the form of a bar chart. HAC will be the dominant species because it is a weak acid, which means it will not largely deprotonate at equilibrium conditions. It will not dissociate by a huge extent at equilibrium conditions. So there will not be a lot of AC minus compared to HAC. Let's now perturb the equilibrium a little bit and add in a strong base, such as sodium hydroxide. And we can add that in dropwise. Sodium hydroxide is a great source of the hydroxide ion, and ask yourself what's going to happen when these two mix. Well, bases and acids neutralize, so if you were to add in drop by drop sodium hydroxide, it will be intercepted by an acetic acid molecule, and they will react to form AC minus and an equivalent of H2O. This process, by the way, is linear. We add in 10 hydroxide ions, 10 acetic acid molecules will get neutralized. If we do 100 million moles, then 100 million moles will also be neutralized. Let me now direct your attention to the data we would churn out from such an experiment, shown in this graph over here. In the x-axis, this will represent the amount of sodium hydroxide added dropwise, and what we are measuring as we go down the x-axis, adding more and more base, what we will be measuring is the concentration of the hydronium ions, aka the pH. And this is the confusing thing. This is not a linear function. pH rises drastically at the beginning of this experiment from very low pHs. Then as we approach this blue zone, the rate at which pH increases levels off a little bit. And then we reach this inflection point where then the rate at which pH/basicity goes up starts to increase again. And past the blue point, the rate at which pH rises skyrockets once more. We can circle back to this diagram to find out why that's the case. In the beginning of this experiment, because we're starting at such low pHs, there is a lot of H+ hydronium. So what happens is when we generate this AC minus, it is very quickly intercepted by the abundance of hydronium in solution, and we reconvert it back into an acetic acid molecule. And we're essentially recycling. It can intercept another incoming hydroxide. So this begins to deplete quite rapidly. As we approach the blue zone of this graph over here, our reservoir of H+ becomes noticeably deficient. It's not empty, but it's not going to be as quick to refill our HAC reserves. So what happens is the hydroxide onslaught continues, and this concentration begins to go down a little bit. And we start to accumulate AC minus. And we can see that over here. You can appreciate it as the two bar graphs beginning to level off. We are effectively converting a strong base into a weak base. And this explains why the pH is still increasing, but it is increasing at a much lesser rate. The acetate is kind of acting like pH breaks now that our hydronium pool is slowly beginning to suffer. And something special happens when we get to the halfway point through this blue zone of stability. And that is the concentrations of HAC and AC minus become equal. And look at that. The pH where the protonated and deprotonated forms match up is 4.76. And we learned from last slide that the pKa, coincidentally, of acetic acid is also 4.76. So this inflection point, where pH equals pKa, it also corresponds to the pH where the protonated and deprotonated forms are equal. And something else interesting is happening. Before the inflection point, the magnitude of the slope of the pH curve is going down. Past it, the slope is going to start slowly going back up again. And the reason why is because at this point, we're starting to run out of HAC. There's only so much that the acetate can take the bullet for, so to speak. And as we keep on adding more OH minus, this system, this cycle will be stressed further and further until we, of course, break this buffer cycle and reach the point where HAC is practically absent and cannot effectively intercept the incoming OH. And at that point, we feel the full effects of the strong base and the pH begins to skyrocket again. So the key takeaways here is that the presence of a weak acid in combination with its weak conjugate base provides us a buffering zone where changes in the pH are pretty mild. And you can see hopefully from this graph that the sweet spot is going to be plus or minus 1 pH unit from the pKa of the dissolved weak acid. And this system works both ways, by the way. If we did the opposite and added acid from a base into a basic leaning solution, well, then the acetate can intercept and mitigate the resulting pH drop from this onslaught of hydronium. So long as we have both weak acid and conjugate present to some degree, we can resist pH changes in either direction. And that is exactly what a buffer is meant to do. I now want to talk about the Henderson-Hasselbalch equation. This equation is going to become your best friend. It was derived decades ago by taking the negative log of the Ka equilibrium expression shown over here. This is the equation that we used in that ice chart 2 slides back, and you can follow through on your own if you want to see how taking the negative log of both sides will rearrange the terms until we get to the Henderson-Hasselbalch equation, which I have reproduced below in that blue bubble. I'll remind you that I do not test people on mathematical derivations in this course. I just outlined the steps here for funsies, basically. What I do want you to know is how the Henderson-Hasselbalch equation works. How the pH equals the pKa of a buffer component plus the log of A minus divided by HA, or the concentration ratios between deprotonated and protonated, or the conjugate base with its corresponding acid. This equation tells you what the pH will be for your buffer depending upon how much of column 1 and column 2 you mix into the solution. The Henderson-Hasselbalch equation is the solution to this curve that runs through the titration plots. This nonlinear function. The Henderson-Hasselbalch equation is incredibly useful, and there's a lot of, mathematical beauty in it, in my opinion, because remember what I said before about how the pKa is the pH, where the concentration of acid will equal the concentration of its conjugate base. This equation proves it. We don't have to have any concrete numbers in our back pocket. If it was an X molar solution of acetic acid, let's say, 1/2 of X at this inflection point will be in the acid form. The other half will be in the basic form, and anything divided by itself is going to be 1. What is the log of 1? The log of 1 is 0. So this entire term drops out at this very specific condition. And what does the Henderson-Hasselbalch equation reduce to? Oh, look, pH equals pKa. This is a really powerful fact that I want you to internalize. The pKa is the pH where the concentrations of protonated and deprotonated forms are equal. All right, now I will reiterate that it is a commonly accepted rule that plus or minus 1 pH unit off of your buffer's pKa will correspond to the buffering zone of your solution, okay? The area where it is considered most pH stable, the area where your buffer is actually working, all right? And we're going to use the Henderson-Hasselbalch equation to find out why. Over here, I have the Henderson-Hasselbalch equation written out like this, where I just spelt out conjugate base and conjugate acid. And we're going to plug in some numbers to get a feel for what our buffer distribution looks like at both extremes of our buffering region. So pH 3.76 and pH 5.76. So let's start with 5.76, the upper region of our buffering window. The pH, I'm telling you, is 5.76, so we'll plug that in. The pKa for acetic acid is still 4.76. See, off by 1. Plus the log of, oh dear, we don't really know the concentrations of conjugate base or conjugate acid. I guess I never got around to making up numbers for those. Who cares? Let's just throw in a big X for now and not sweat about it. Okay? Hardest math you'll ever do in this lecture. 5.76 minus 4.76, that equals 1. Okay? The log of x equals 1. Well, what does x equal? You don't even need your calculators for this. X equals 10. Another way to write 10 is 10 over 1. And look at that. We don't have concrete values like millimolar quantities for conjugate base and conjugate acid, but what we do know is that the base outnumbers the acid tenfold at the pH of 5.76. And again, hit the brakes, do a reality check. does this mesh with our overarching knowledge of acids and bases? We are in the part of the graph where we're almost fully titrated, okay? We've added in a lot of hydroxide. So you would imagine that we've exhausted quite a bit of our acetic acid. That is why the conjugate acid is so small and the conjugate base is much larger. And as we go beyond this buffering point, that numerator is going to skyrocket. If we were to wind it up and do the Henderson-Hasselbalch equation again, this time we are going to do it on the more acidic scenario at this point, 3.76. What does the ratio of conjugate base to conjugate acid look like now? Pause the video and predict before you follow along. I know I have a prediction, but let's see it through. 3.76 is the actual pH of the environment. The pKa of acetic acid is still 4.76. Plus the log, again, of big X. Some ratio, we'll figure it out. 3-ish minus 4-ish is exactly -1 equals the log of X. The log of X that equals -1 equals 0.1, or 1/10. Look at that. When we start having predominantly acid, we have not titrated very far along our titration curve. We haven't really exhausted a lot of our conjugate acid yet. We've barely started to generate conjugate base that can appear and help us hit the brakes, basically. So that's why the ratio of acid in this case greatly exceeds that of the base. And this is why we consider this to be the upper and lower bounds at which the buffer is going to be useful, because south of this point, like, we're hardly going to have any base to work with to help kick in the brakes. North of the upper limit, we've pretty much spent up all our acid and we've just got base. Base can't neutralize the incoming hydroxide. So you can see, hopefully, here in a more mathematical sense, why the buffering region is so important. I'm going to now demonstrate to you how to prepare a typical buffer solution using a mixture of the free acid with its conjugate base. All right, let's say we want a 100 millimolar solution that is pH 5, okay? And again, let's use this acetate buffer system that we're growing quite fond of, okay? We will be using acetic acid and sodium acetate and some combination that will help us dial in to the exact pH that we want, which is 5, okay? So we're going to go through this calculation step by step. All right, the Henderson-Hasselbalch equation is going to come into clutch here. We are going to put in 5.00 as the desired pH. We already know that the pKa, it's going to be burned into your souls at this point, is 4.76 for acetic acid. Plus the log of A minus over HA. All right? Oh no, these are two different variables. You can't solve an equation that has an x and a y in it, right? So let's just again call this big X. Big X will represent the ratio, and then we'll worry about the actual numbers later. All right? So let's do the fun part, subtracting the pH and the pKa. That's going to give us 0.24 equals log of what I like to call big X. All right? This is doable. How do we solve for the log of X? Think back to the last lecture, all right? All you need to do is just put everything to the power of 10, all right? I'm going to go 10 to the power of 0.24, all right? Which will equal 1.74. This equals the ratio of acetate to acetic acid, all right? So think this through. We are getting a number that is greater than 1, which means the base must outnumber the free acid. And this makes sense because our target pH is north of our pKa value. All right? If we're higher than the pKa value, then we have more base than acid presence. Okay? So, I'm just going to write that out again over here because this can be conceptually quite difficult. If the concentration of acetic acid equals X, let's say, then that must mean we have more acetates than acetic acid. Specifically, we have 1.74 times the amount of acetic acid. Okay? Now we can build up a system of equations because we've expressed everything in the terms of one variable, X. Our goal is to make a pH 5 solution that is 100 millimolar of acetic acid and sodium acetate. The 100 millimolar is going to go over here, and some combination, X plus 1.74X, which corresponds again with acetic acid and acetate. All right? Do a little bit of factoring. We can factor out an X from this side of the equation. X equals 1 plus 1.74. This is a little bit of a neat hack if you're a little rusty with your algebra. All right? And if you're not sure how I did that, just do the reverse. Factor in X over here to that side of the binomial, and then X again over there to 1.74, and you get X plus 1.74X again. Okay? This, of course, again, really difficult math, equals 2.74. And all you have to do now is divide both sides by 2.74. And this will give you the value of X. X equals 36.5 millimolar. All right? That corresponds to acetic acid. Acetate is 1.74 times that amount, times X. Just put into your calculators 36.5 times 1.74, and the answer is 63.5 millimolar. Oh, I wanted a different color. And that's how we get from here to there. Yes, it is a lot and it is quite laborious and it involves some, moderate level algebra. Okay? A great self-check. I'm all about asking ourselves, does our answer make sense? If you add up if you add up 36.5 and 63.5, you should get something exactly, if not very close to 100. If you're a little bit off, that's probably rounding error. We're dealing with logarithms here. But if you are not even close to 100, you did something wrong, burn it all down, and try again. The acetate system is really convenient to use when introducing these buffer type calculations because it is a monoprotic acid, which means it only has one acidic proton that can be removed. Okay? However, the reality is that there are a plethora of compounds out there, synthetic, natural, buffer, or a metabolic intermediate that have multiple groups that can be protonated or deprotonated. And the word for these compounds are called polyprotic acids. Okay? And these are really quite ubiquitous. And the important thing for you to know is that protonation and deprotonation proceeds sequentially, okay, in these polyprotic acid cases. Let's consider phosphates, the phosphate system, as an example in this chart, which only contains a few of the several polyprotic acids out there. Okay, when we start in maximally acidic conditions, okay, like let's say we just have a jar of phosphoric acid, okay, it's mostly going to be H3PO4 neutral. We start titrating in base, like in the form of hydroxide, we start increasing the pH. All right, around 2.14, are we going to see a noticeable titration of the first acidic proton, driving H3PO4 into H2PO4 minus and H plus. Okay? And that is going to be the first deprotonation product that we form. Only after we've completely removed that first proton from all phosphoric acids in solution can we then start working on the next one, an H2PO4 minus, and this will have a pKa around 6.86. And over here, this is where we start to see the next proton come off to form HPO4 2 minus and another equivalent of a proton, as the number of these hydroxyl groups starts proliferating in the solution. And that last one is really hard to pull off. We need a lot of hydroxide to coax it off at a pH of 12.4. And only then do we go from what's called the dibasic salt to the tribasic one, where we've stripped the final protonatable group from the HPO4 2 minus. Okay? So the key here is that notice how it happens. 1, 2, 3. Sequential removal. They all don't get ripped off simultaneously. Okay? And there's quite a few pH units difference between each stage. Let's go back to our friend MOPS here to use as a concrete example to illustrate how the different species of protonated or deprotonated buffers changes as we do a titration experiment, okay? So what I've done here is show you a titration curve of MOPS, all right? And on the x-axis, again, we will be systematically increasing the NaOH content by titrating it in drop by drop. And in the y-axis, we will measure the pH of the entire solution. All right? And I've reproduced over here the molecular structure for MOPS, all right? But if you notice, they're all in different protonation states. How do these protonation states change? Well, let's start at the beginning of our titration experiment, right over here where there's a heart, okay? And at the hearts, we have practically no base in the solution, and it is quite acidic, okay? So think of it this way. What do our surroundings look like? It's an onslaught of hydronium, hydronium, hydronium all around us, okay? These hydroniums are creating like a proton pressure, if you will, and they've got nowhere to go. So where do they end up? They're getting shoved on and slapped on to our titratable groups, the sulfonates and this tertiary amine. And I'll remind you that their pKa's are 3 and 7.2. Okay, so there's just protons galore, hence we are maximally protonated at acidic pHs. I'll repeat that. We are maximally protonated at acidic pHs. Important to know. Beat that in your head. Now let's turn on the hydronium vacuum, aka add in sodium hydroxide, neutralize some of this stuff. All right, there's a few H pluses hanging out, but there's also some OHs, right? So what starts happening, these OHs are going to start ripping off and plucking protons off of our MOPS molecule. And which one do you think is easiest to pry off? Is it easiest to remove the proton with the pKa of 3? Or would it be easier to remove the proton with the pKa of 7.2? The lower the pKa, the more acidic that moiety or functional group is. So that would mean the sulfonate is more acidic, and it's going to relinquish those protons more easily. And look what we have here. We start to generate these negatively charged sulfonates. Pay attention to that because of the hydroxides neutralizing that part of the molecule. Now, how would you describe the protonation state at 0.5 equivalents sodium hydroxide right over here? Well, look at the graph. We're going to go ... follow up, and we are in the middle of the plateau region or the buffering zone region. We're going to move over to the y-axis, and oh look, the pH value is 3. And when the pH equals the pKa, half of that group is protonated and half of the group is deprotonated. So we are 50% heart and 50% star. Half of these sulfonates have deprotonated at this point. You want to know which point 100% of them get deprotonated? When we add in 1 equivalent of sodium hydroxide, okay? Because 1 equivalent of that will annihilate the 1 equivalent of MOPS, specifically the more acidic group. So it will be 100% star at 1 equivalence of NaOH, which is in the middle of this inflection point, the steepest part of the curve, the least stable parts. Here, we're going to make a transition. We've completely run out of sulfonates to deprotonates, but the hydroxides keep on coming. And so what are they going to do? They're going to start attacking the only other titratable group that's left. That is right. It's going to be this guy. So hydroxide hydroxide, hydroxide all around. And what's going to start to happen is we're going to slowly deprotonate the last group, the amine, the least acidic, most basic part of the MOPS molecule. It requires a lot more hydroxide to pry that off, but here we start to do it. And if we ask ourselves what happens at 1.5 equivalents of sodium hydroxide, follow the line up, and look, we're in the middle of the plateau region, and this corresponds to 7.2 on the pH axis. And when pH equals pKa, A minus equals HA. Okay, at 1.5 equivalents, the star configuration will be equivalent to what I'm calling the horseshoe configuration over here. We're half out of the protons on this group. And as we keep on adding in base, by the time we reach 2 equivalents, all of this is now gone. And we are 100% horseshoe. We have broken away from our buffering zone yet again. And from this point on, hydroxide is just going to cause the pH to skyrocket and make it go through the roof. There's a lot going on in this slide, but this is really important to think about the systematic way in which polyprotic entities undergo acid-base reactions with their environment. I frankly recommend you pause and watch this slide again, because stuff like this is not going to go away in the course of biochemistry. I want to end on a final word of caution. The concept of pKa is really tricky. They're complicated. I want you to consider something though. pKa's are used as constants in these equations like ice charts and the Henderson-Hasselbalch equation, but they're actually not that constant. pKa's can and will in this course vary greatly. The things that can mess up a pKa are stuff like temperature, ionic strength, which I mentioned in the previous slide, different solvents. The pKa could be one number in ethanol, another number in water, another number in DMSO. The neighboring atoms and functional groups will also alter the pKa's. And something called the chemical context, or just the general surroundings, if you will, other molecules that are nearby. And these last two items we're going to highlight in the following question. We're going to circle back for a final time to our friend MOPS buffer. This is the molecular structure. The morpholinoamine over here has the pKa of 7.2. Okay, well, let's look at a similar goods buffer called MES buffer. MES looks pretty identical. The only difference is we've lost a methylene group. So this chain is shorter going from MOPS to MES. I'm going to ask you two questions. Of these two functional groups, which is the more acidic amine? Which is the more basic amine? Think about that. And then ask yourself, why are they different? Why is this pKa a whole unit larger just because this tail is longer? I'm going to let you think about that and let that haunt you until next time. Goodbye, everyone.